Hello, this lecture is on diffusion. Why are we studying diffusion? In the previous chapter or module, we learnt how introducing defects into crystals can enhance the material properties. What we want to understand now is that when we add a second type of atom into a crystal lattice, we'd like to know how those atoms get distributed and what the concentration profiles will be. And that's why we need to know about diffusion. So what is diffusion? Diffusion is the spontaneous mixing of particles that occurs due to thermal energy. In this glass of water, an ink drop has been placed into it. And we know that after time, the ink will slowly distribute itself until the concentration is uniform. We have to ask ourselves, why does this happen? The reason it happens is due to a phenomenon called random walk. Random walk is the random motion of particles driven by their thermal energy. Here we see a simulation, a computer simulation, where the particle starts off at the origin and the computer generates a random step in any direction. The step length is shown by the length of the straight line, and then where you see the kinks, it has recalculated the next step in a random direction. And we see that when we do the math of the random walk, the average displacement of the atom or the particle is not zero. And if you like, you can go to the link I've shown on the slides here, and you can do your own simulations. Diffusion also occurs in the solid state, although of course it occurs much slower than it would in a liquid or a gas, due to the difficulty of atoms moving in the solid state. Let's have a look at this diagram here. It's showing pure copper which has been put into contact with pure nickel. If we look at the concentration profile of copper, we get a sharp transition from the pure copper to the pure nickel. However, if we heated this junction up, after some time, some of the copper atoms would migrate into the nickel, and some of the nickel would migrate into the copper, purely due to random mixing or random motion. The system is going into a more probable state. It's more probable for the atoms to get mixed up rather than stay on their separate sides. And here we see a hypothetical concentration profile showing how the percentage of copper drops more smoothly after diffusion has occurred. And after a long period of time, we would get uniform distribution of the copper within the material. I talked about the difficulty of diffusion in the solid state due to the difficulty of atoms being able to move around within the crystal structure. Let's have a look at some mechanisms of how atoms can move in a crystal structure. One of those mechanisms is due to the presence of vacancies. If there's a vacancy, that means an atom can move into that an adjacent vacancy. An analogy to vacancy diffusion is a sliding tile puzzle. In a sliding tile puzzle, we have some tiles here. We have 8 tiles, and we can slide them around because we have a vacancy. So the object, of course, is to get these in numerical order, and I can do that because there is a missing tile here. So for instance, the 7 can slide across, allowing the 1 to finally get into position. So we can see how an atom can move through a lattice because of the presence of a vacancy. Another method of diffusion is interstitial diffusion. This occurs when the diffusing species or atom is much smaller than the atoms in the host crystal and can fit into the interstices and move between them. We are now going to look at the mathematics of diffusion. In particular, fixed laws. This law concerns the case of an equilibrium situation. Also known as the steady state conditions. What this is basically saying is that J, which is the flux of particles of the diffusing species, flux is the number of particles crossing an area in a unit amount of time, or per time interval. In this equation, we see that the flux is equal to d, which is the diffusion coefficient, multiplied by the gradient of the concentration. And there's a negative here, and that means that the particles want to flow in the direction of falling concentration gradient. So this is a very precise way of saying that the particles want to move from a high concentration area to a low concentration area. And this quantifies exactly how much flow occurs. So let's have a look at the equation in more detail. For fixed first law, which we must remind ourselves is for steady state conditions where the concentration C is not changing with time, and so the system has reached an equilibrium condition. J is known as flux, and it's the number of solute particles crossing per unit area per unit time. D is the diffusion coefficient, a constant that must be determined for the system. And it's not exactly a constant, it is dependent upon temperature, among other things. C is the concentration of the solute, and X is the position along the axis of the one-dimensional flow. We mustn't forget the minus here, because it tells us that the flux, the flow of particles, is in the direction of the falling concentration gradient. To demonstrate how to apply this equation, let's have a look at this textbook problem. The purification of hydrogen gas by diffusion through a palladium sheet was discussed in section 5.3. Okay. Compute the number of kilograms of hydrogen that pass per hour through a 5 mm thick sheet of palladium having an area of 0.2 meters squared at 500 degrees centigrade. Assume a diffusion coefficient of 1 times 10 to the minus 8 meters squared per second. That the concentration at the high and low pressure sides of the plate are 2.4 and 0.6 kilograms of hydrogen per cubic meter of palladium, and that steady state conditions have been attained. To solve the problem, let's make a sketch to help us think about the quantities involved. We have a piece of palladium metal. Let's set up a coordinate system for the diffusion. This is 0, this is 5 millimeters. We have hydrogen flowing in, and there's going to be a flux of hydrogen. We are going to assume steady state. We know the concentration in the high pressure side. So this is the high pressure side, and this is the low pressure. So the gas is moving from high pressure to low pressure, and the hydrogen is dissociating. So the hydrogen starts off here, it dissociates, travels through the metal, and then recombines to form hydrogen gas at the other side. Says here, compute the number of kilograms of hydrogen that pass per hour through the 5 millimeter thick sheet of palladium. So what we'd like to calculate is the flow rate per hour. So J, well, that's not quite J, because remember J is the flow rate per unit area. If I were to draw this in 3 dimensions, we know that the cross-sectional area represented by this hatched area here, the area is given as 0.2 meters squared in the problem. It says it right here. Okay, temperature is 500 degrees centigrade. That doesn't seem to be significant because they give us the diffusion coefficient already. In order to solve this problem, first we need to find the flux. If we know the flux, and we can calculate that in terms of, or using, by applying Fick's first law. Now let's draw a sketch of what we expect the concentration profile to look like. It starts off here in the high pressure side at, it says here 2.4 kg per meter cubed. So it starts off here 2.4. Sorry, I'm having problems sketching this neatly. 2.4 kilograms per meter cubed, and that drops down to 0.6 kg per meter cubed as we go through the material. So let's say this, if this is x equals 0, and this is x is 5 millimeters. What does the curve look like as we go from our initial concentration on one side to the final concentration? Well, the way that we can solve this is to realize that we're in a steady state situation. In a steady state situation, the concentration is not changing. That means that for any particular part of the metal, the amount of hydrogen entering this cube must equal the amount leaving. And that is dependent upon the flux. Hence, the flux through the material is constant. The only way the flux could be constant is if the gradient were constant. What does a line with a constant gradient look like? It must be a straight line. So now we know, I'm just going to draw between the 2 points in the metal. This is supposed to be a straight line. So now we know that the concentration profile must be a straight line in the material. And so it's an easy job now to calculate dc dx. So I'm just going to divide the page in two here. dc dx is the rise over the run. It's one way it's taught. But we don't have a rise as x increases. What do we have? Okay, we actually have a drop. And that drop can be given by taking the final value minus the initial value. So we get a negative value for the rise. It is a negative gradient. And dividing that by the distance. The distance is given in millimeters. And let's have a look at what units d is given in, so we can use the appropriate units for the distance. We see the diffusion coefficient is given in units of meters squared per second. Hence, for our distance here, we should use meters. 0.005. Okay, that's meters. And this will give us the concentration gradient, which is equal to, work that out on my calculator. It's equal to minus 1.8 divided by 0.005. Okay, that's minus 3.6 times 10 to the 2, and the units we will have is kilograms per meter to the power 4. Okay, we have that. Now we can calculate the flux. The constant flux in the material is minus d multiplied by the gradient, the concentration gradient. D is given as 1 times 10 to the minus 8. The gradient is minus 3.6 times 10 to the 2. So what we have now, the negatives cancel, and we have a flux, positive flux through the material, 3.6 times 10 to the minus 6 kilograms per meter square. So that's the flux. Let's calculate the flow rate now. The flow rate for the area given is going to equal the flux, because the flux is per square meter, times the area, which is equal to 3.6 times 10 to the minus 6 times 0.2 meters squared. So let's work that out. Okay, so I have minus 7.2 times 10 to the minus 7. But if I want, that's per second, that's going to be per second. So that's equal to 7.2 times 10 to the minus 7 kilograms per second. Just insert another page. Okay, now I have that. What I'd like to do is calculate the hourly flow rate. And that's simply going to equal the flow rate per second multiplied by 3,600 seconds per hour. Okay, and I get an answer of 2.59 times 10 to the minus 3 kg per hour. Okay, and that would be the flow rate of the hydrogen per hour for the area of the palladium given. The diffusion coefficient is dependent upon temperature according to the equations shown, which has a form that is very common for thermally activated phenomena. The diffusion coefficient at a certain temperature is going to equal d sub naught, which is a pre-exponential term, e raised to the power of minus q sub d. Q sub d is the activation energy for diffusion per particle, divided by kBT, where kB is a Boltzmann constant and T is the temperature in Kelvin. We may alternatively have the activation energy for diffusion per mole of particles, in which case we divide by the gas constant multiplied by the temperature. The temperature must be in a thermodynamic temperature scale, so typically we use Kelvin for that. If we take the natural logarithm of both sides of this equation, we can linearize it. So if we do that, we get the natural logarithm of the diffusion coefficient is equal to the natural logarithm of the pre-exponential term minus qd over kBt. Hence, plotting the logarithm of the diffusion coefficient versus the reciprocal of temperature will give us a straight line with a negative slope. And here it is. This is for carbon and graphite. Here we have calcium in calcium oxide, magnesium in magnesium oxide. And here we have a very technologically important diffusion couple. Well, this is actually for self-diffusion of iron in BCC iron, which is a low temperature crystal structure that iron has at low temperatures, I should say. And at this particular temperature, what happens, it undergoes a transition into an FCC crystal structure, and so we see a discontinuity in the diffusion coefficient. As the temperature increases, the reciprocal reduces, and we can see that with reducing reciprocal value, the diffusion coefficient increases, which is what we expect, because with the greater the thermal agitation, the greater the mixing, or the greater the rate at which mixing occurs, and that is the driving force for diffusion. Let's now look at non-steady state situations where the concentration of the diffusing species in the material is dependent upon time, so it hasn't reached a constant value. In such cases, Fick's second law applies, and this is more difficult to apply, but we're going to look at a very simple but practical situation of atoms in a gas penetrating the surface of a solid, and this finds widespread application in fields such as surface hardening of materials such as steels, and also for semiconductor manufacture. So imagine we have a gas shown in yellow here, where the concentration of the gas, which would give the concentration of the diffusing species at the surface, is given by C sub S. Inside the surface, the surface being of the material being shown by the solid black line, inside the surface, the initial solute concentration is C sub 0. We would like to find the concentration of the diffusing species at a particular depth, x. We can do so with this equation, which is the solution for Fick's second law for this situation. The solution is, in more detail, is that the C sub x, which is the concentration of the solute at depth x below the surface, minus C sub 0, which is the initial concentration of the solute in the solid, divided by C sub S, which is the concentration of solute at the surface, minus C sub 0 is going to equal 1 minus ERF. ERF is the error function of this parameter, and the parameter is x, the distance, divided by 2 multiplied by the square root of the diffusion coefficient multiplied by the time over which the diffusing species has been allowed to diffuse. So we can see that the concentration is a function of depth and a function of the time given for diffusion to occur, and also temperature, because temperature affects the value of D. Error functions are typically tabulated, and here I've shown an excerpt of some values of the error function for some values of the parameter here shown as are given the variable z. I'm going to show you how to apply what we've just learned to a particular problem here. It says determine the carburizing time. Carburizing is the process where the concentration of carbon at the surface of a piece of steel is raised in order to harden the surface. Harden the surface increases wear resistance. So this would be a heat treatment process that would be appropriate for giving a hard wearing surface, such as you might want to do with a gear surface or similar kind of machine component. It says here, determine the carburizing time necessary to achieve a carbon concentration of 0.4 weight% at a position 2 millimeters into an iron carbon alloy that initially contains 0.2 weight% carbon. The surface concentration is to be maintained at 1.3 weight% carbon, and the treatment is to be conducted at 1000 degrees centigrade. Use the diffusion data for gamma iron in table 5.2. Okay, I hope I've included that data in here. Seems like I haven't. So I will go back and find that data and insert it. So here they want us to look at the diffusion of carbon in gamma iron. We have the pre-exponential term is equal to 2.3 times 10 to the minus 5 meters squared per second, and activation energies given in both kilojoules per mole and EV per atom. So let's try and use that data to solve this problem. Let's extract the essential information here. Let's get in the right pen. Okay, so we know that the equation is Cx minus C0 over Cs minus C0 is equal to 1 minus the error function of x over 2 root dt. Okay, so what we have to do now is determine the carburizing time necessary. So we're trying to find T. Okay, and they tell us that the surface concentration, we want the carbon concentration to be 0.45 at a position 2 millimeters into the iron. I noticed that all my units for length, for instance in the diffusion coefficients, are in meters include meters. So I'll be using meters for any lengths for that purpose. So what we know now is that Cx is the required concentration at the depth, which is 0.45, as you can see, we have this concentrations on top and on the bottom. So if we use the same units, we don't have to convert to any particular units. The units cancel out. So we have 0.4 weight percent, 0.45, sorry. C0, that is the concentration of carbon in the material initially, which is 0.2. And CS is the concentration at the surface, which they tell us is 1.3. Okay, so now we can definitely do the first part. Divide up the page here. So therefore 0.45 minus 0.2 divided by 1.3 minus 0.2 is going to equal 1 minus the error function of x over 2 root dt. So working out what that is, we get that this part of the expression on the left is equal to 0.227, and that's equal to 1 minus the error function of x over 2 multiplied by the square root of dt. Rearranging, we get the error function of x over 2 multiplied by the square root of dt is equal to 0.773. What we're going to do now is do the inverse error function of both sides. And to do that, we can use this table. So we want to find for what value of the parameter do we get an error function of 0.773. Well, it's pretty close to this. I'm pretty close. That's close enough to 0.773. And so the value of the parameter inside the error function is 0.85. So therefore, 0.85 must be equal to x over 2 dt. Okay, we know what x is. It's equal to 2 millimeters. Okay, so now we know that the square root of d times t is equal to, was it 2 millimeters? That was right? Yes, 2 millimeters. 0.002 divided by 0.85 multiplied by 2. And we get for that 0.002 divided by 0.85 multiplied by 2 that's equal to, it's got to convert that in scientific format, 1.18 times 10 to the minus 3. I'm going to square both sides now. Therefore, d times t must equal 1.38 times 10 to the minus 6. First, well, we must now try to calculate what is d. We know the temperature is 1000 degrees centigrade. So in order to calculate d, d is equal to d naught e to the minus q over, we could use either really. I can use RT, okay, where Q is going to be the activation energy per mole. The temperature is 1000 degrees centigrade, plus we have to convert that to Kelvin. In order to convert that to Kelvin, we have to add 273. So that's the degrees to Kelvin conversion. So now we get 1273 Kelvin. We can now plug that into this formula, into the formula for D. So D is going to equal D sub 0, and we can get that from here. D sub 0, and there's kilojoules per mole. Okay, so we'll have to multiply that by 1,000 to convert that into joules. So D naught is 2.3 times 10 to the minus 5. And then EXP 148,000. Divided by R, which is 8.314. You can look that up. It's the ideal gas constant. Multiplied by 1273 Kelvin, and that must all be raised to the minus. Haven't really laid it out very well there, so I'm going to do that again underneath so it's clearer. Okay, so in this way we can calculate what D is and substitute into, I should have numbered some of these equations here, perhaps call this 1, call this 2. If I substitute D from equation 3 into equation 2, I can find the time required for diffusion to occur. And so we can design our heat treatment process. Let's look at some engineering applications of what we have just learned. One extremely interesting application of diffusion theory is in computer chip manufacture, and I would encourage you to watch the video that is shown by the link below, and that you can also find included in the slides for the course or for this module. Also related to manufacture of chips is this idea of diffusion bonding of gold. And there's a video here showing a machine that can bond gold wires onto gold films by using a heat that is much lower than the melting temperature of gold. And so I'd encourage you to look at that video as well. And diffusion bonding of gold is actually a very ancient technique, used to create gold artifacts. We can also find examples of diffusion in the creation of ceramics. The way a ceramic is generally made, or one way in which to make it, the very common way in fact, is to start off with a powder of the inorganic compound that we wish to make a solid block out of. Then we compact this powder. Very, very similar to making household ceramic items. We start off with the clay. What is clay but simply just very fine particles that are suspended in water. We can shape this clay, but if we dry it and dry off the water, we end up with a material that is still brittle and will break and is not waterproof. If we put water on dry clay, it will start to soften again. However, if we put the compacted product into a high temperature environment and allow for diffusion to occur between the particles that comprise it, we will get very strong bonds created between those particles. And that's what firing does to clay articles, and now we get a strong waterproof material. Another very interesting application of what we've just learned is surface hardening of steels and other materials. Here we see a gear wheel that is being surface hardened. So a gear must be both tough, it must be able to resist shocks and must not crack generally. However, the surface of it must be hard and resist wear if it is to have a long life and lower resistance. If we were to make the entire gear hard, it would also be brittle and the entire thing could shatter. So what we do, we confine the hardness just to the surface of the gear by using a process called nitriding, where we embed nitrogen into, or diffuse nitrogen into the surface of the material, which hardens it just at the surface. And a very interesting way to do that is called plasma nitriding. And you can see here how the ions are creating a plasma around this this gear object, creating a characteristic purple glow for nitrogen. If you can watch the video here to show you an example of a process by a firm that perform nitriding. There are many other examples, some of which we'll cover in the practice problems. Thank you very much.